Hello there, welcome to another problem session. This is problem number 2 today I'm doing. So this is a interesting problem actually. It's a not very hard problem, but because of the way it's set up, it looks like a hard problem. So we have a infinitely long wire. This is go to as long as you want and as long as you want that way. And then there is a structure sitting here, except that this part, this part can slide over this part, and the whole resistance for entire thing is R. Is placed here, but you can say this is nearly resistance-less, and the whole capacitance of this structure with respect to these wires, is C0. Okay, so what happens when this sliding? The magnetic field is produced by this guy, and it's let's draw them some magnetic field lines. It's going to be like that. So these magnetic field lines are actually going through this area, So if I take this as a loop, then I would have Ampere's law. Let's call it use A, B, C, D. So that's my loop, and let's see if I do DL that way. So DL is that way over here, and DL is that way over here, and the DL is that way over here. So yeah, I'm going in that direction. So if I do the DL, so then this loop, the normal will be perpendicular to in that direction because of the right-hand rule. So the Faraday law, you may remember that is a, you can say EMF, induced EMF in this loop is equal to minus E dot DL. So that's induced EMF, and this minus with this goes to the plus, and this is an oriented loop with a direction in it. And so area over this area, that's the loop, I have a d dt of this integral b dot n hat dA, and this n hat and this orientation of the loop, they're kind of related with right-hand rule. So that's the Faraday law. Okay, so we're supposed to find, given these numerical values, we're supposed to find what's the maximum current through R. So this is this two choices, and then there's what's the maximum this here. So what's going on is the entire EMF, if suppose a DC battery, then you'll have if the entire EMF falls across this, then I'll have a maximum current. So this is choice between entire EMF over R. Which one is this? Okay, so that will be the maximum current. And if the entire EMF falls across this capacitance, then we'll have a maximum charge on the capacitance. So Q equals to CV, right? So C times this will be the Q max. So these are the two formulas we can use, but then we basically find the induced EMF. Now, the way we are doing in this is how to find this. The way we are thinking about that is the limit delta t goes to 0, and do this integral b dot n hat dA at a time t plus delta t, and subtract away b dot n hat dA at time t. So we need to imagine two nearby times and then compare that, right? So say this is time t. When it moves up, let's redraw it. Okay, let's redraw it. Let's redraw it. So I have this more. So when this is a time t, and this is time t plus delta t. So you can see that the new area is just basically this rectangular over this rectangle. That's the change, right? And so here is a current. So this will be the numerator. So numerator will come from doing this integral over this. So if this is, say this is A and this is B, and this is some arbitrary point, and this is the, let's call this axis X. So at X, B is pointed down, B is going in, so B is going in, n hat is coming out. So this will be, if I look at some S, or maybe X, and then this little thing is dx. So through this area, you'll have a b dot n hat at x of the height will be v times delta t, right? Because it's moving with the speed v. So this distance traveled would be v times delta t. So v times delta t times dx. So that's the dA. And this will become a distance x from there. B at that point will be a distance x from current carrying wire. So it's going to be mu naught over 2 pi, mu naught I over 2 pi x. So this will be minus mu naught I over 2 pi x. Minus because they're in the opposite direction, so angle between them is if you're very much like that, then you can do this and you have a n hat and cosine the angle between them, which is 180 degrees. So this is 1, and so this becomes minus. That's why it's minus. So this is the integrand, and so numerator is minus of this, and integrate over x going from a to b, So this is minus mu naught I over 2 pi, and the v comes out, delta t comes out, and then you have a log b over a. So okay, so that's, so EMF induced, and we don't need to know the direction of it, so we can just look at to decide between these two. There's no direction required, so this is just going to be this divided by delta t go to 0, delta t cancels out, so this cancels out, so it's just going to be mu naught I over 2 pi log b over a. Let's let's do the numerical part. So it says the mu naught is 4 pi times 10 minus 7. That's true. So this is 2 times 10 to the power minus 7 SI units, and I is 2 amps, and then log b, this distance is 4, distance is 1. So 4 centimeter over 1 centimeter. So I don't need to change units there. And so this is like a 2 square. And so that becomes 4, and this becomes 8 times 10 to the power minus 7 log 2. And they give you log 2 is 0.7. So this is 8 times 0.7 times 10 to the minus 7. And so EMF just turns out to be point, no, 5.6. 5.6 times 10 to the power minus 7, and this EMF is going to be in the volts, right? So that now if with this that, then I have to divide by 1.4. So if I divide by 1.4, I think there may be a problem with the, some units here. So let me just go back and pause. I did notice some mistake. I forgot that V over here, and so V is 3 meter per second. So multiply by 3. So this will be 24, and this will be 2.4 times 10 minus 6. Okay, so now it's 1.4. So 2.4 over 1.4 for R. So let me calculate. Okay, so I kind of made a mistake over here. So you're at 24, and 0.7 is 116.8. So that makes it 1.68 times 16 times 7, so 10 to the minus 6 volts. So that's EMF. Let me erase and then work out those numbers, okay? Okay, so EMF is that, then I divide by resistance to decide between these two. So EMF divided by the resistance is 1.68 divided by 1.4 times 10 minus 6 amp, and this thing is 1.2 times 10 minus 6 amp. So A is correct, B is not correct. To decide between C and D, we need C0 is C0 is 5 microvolts. So I just multiply by C0 times EMF. So this is Q max. C0 is 5 microvolt, and it's a microfarad. So this is this many farads times 1.68 times 10 minus 6 volt. These two together will make it a coulomb. So let's call it 7, 8.5. So it will be 8.4 times 10 minus 12 coulombs. So this is going to be this guy. So this is correct, and this is correct, and this is not correct. So that's how you do this problem. Now, before we move on, just look at the direction, whether the current will flow this way or this way. So which way is the induced current? It's not asked in this question. Okay. Okay, so although this is not asked this question, let's try to answer that question. Which way is the current is going to go, this way, or current going to go the opposite? Well, of course, you can use Lenz's law. So you can see one way to use the Lenz's law is to just see if the magnetic flux is increasing, right? So this magnetic flux going in is increasing, which means the induced current will produce going out. Okay, so if the current is this way and use the right hand rule, it's going to produce going out. So it's going in the direction that this thing is. I use the arrow, so it's the same. So this is the induced current direction. Another way to do it is this. Electric field will be in the direction of the induced current. This is the electric field. Electric field and current will be in the same direction, right? So when we work this out, this quantity here, using this thing, this quantity was negative. This actually less than 0. So this actually was minus and minus that EMF we had. Okay, so this actually is positive. You can go back and redo this calculation and you will find that it is positive. So we're using this because n hat was in that direction and the B was in the opposite direction, so, and it was increasing, so this integral of d dt was negative, and so a negative term negative makes it positive, so this is positive, so I is along dl and which is along this, so this also says it's this way. Another thing that you should notice here is that the shape of this doesn't matter. It's a semicircular here, but I could have done completely random shape like that, and even in that shape, if you pull it up, you'll have the same kind of the area is shape. So even if you had a problem like this, where this was like really complicated shape, and this shape was the only thing that was moving, that you can see that at some other time it was like this. So between this and this, the new area that came into being is just this area, so it will still be rectangular. Okay, so the shape was of thing that was moving, not very important in this problem. Okay, just a reminder that if you haven't subscribed, very helpful for you to subscribe so that you can grow this channel. If you like this kind of explanation, please hit the like button. You can also get more from going to my website here. Okay, take care, bye.